Chapter 7, Feedback Control Loop. Now that we have talked about some good understandings of process dynamics previously, we can begin to address the technology for automatic process control. The goals of process control, safety, environmental protection, equipment protection, smooth operation, quality control, and profit, are achieved by maintaining selected plant variables as close as possible to their best conditions. The variability of variables about their best values can be reduced by adjusting selected input variables using feedback control principles. As explained in Chapter 1, feedback makes use of an output of a system in deciding a way to influence the input to that same system, and the technology presented in this part of the book explains how to employ feedback. This chapter builds on the chapters of Part 1 of the book, which were more qualitative and descriptive by establishing the key qualitative aspects of a control system. It is important to emphasize that we are dealing with the control systems, which involves the process and instrumentations, as well as the control calculations. Thus, this chapter begins with a section on the feedback loop in which all elements are discussed. The reasons for control are reviewed, and because engineers should always be prepared to define measures of the effectiveness of their efforts, quantitative measures of control performance are defined for key disturbances. These measures are used throughout the remainder of the book, and because processes usually have several inputs and outputs, initial criteria are given for selecting the variable for a control loop. Finally, several general approaches to feedback control, ranging from manual to automatic methods, are discussed with guidelines for when to employ each type of control. Electronic, manual, control, these are the types, blah blah. 7.2, process and instrumentation elements of a feedback loop. All elements of a feedback loop can affect control performance. In this section, the process of instrumentation elements of a typical loop, excluding the control calculations, are included, and some quantitative information on their dynamics is given. This analysis provides a means for determining which elements for the loop include significant dynamics, and when the dynamics of the fast elements can usually be considered negligible. A typical feedback control shown in 7.1 is shown in 7.1. Okay. This discussion will address each of the loop, beginning with the signal that is sent to the process equipment. This signal could be determined using some feedback principles. Maybe you could use a person, or automatically by computing the variables with a computing device. And some key features of each element in the control loop are summarized in Table 7.1. The feedback signal in Figure 7.1 has a range usually expressed as 0 to 100%, and this is determined by a controller, or it's set manually by a person. However, we have two types of automatic control. We have a pneumatic control system and an electronic control system, and it's just worth noting that the automatic electronic control system is usually not implemented because of the high milliamperes that you would require to control a motor for the valve for the control final element. 7.1 is a process and instrument elements in a typical control loop. Table 7.1, key features of control loop elements excluding the process. Inside of this table, loop element, function, typical range, and typical dynamic responses, controller output, transmission, signal conversion, final elements, and sensors. We can talk about that later. At the process unit, the output signal is used to adjust the final control element. The equipment that is manipulated by the control system is referred to the final control element, and 90% of the time, this final control element is given as a valve. The valve percent opening could be set by an electronic motor, and as I was saying, we don't like the electronic motor. For pneumatic power, this is an alternative. A typical supply is used for compressed air, around 3 to 15 psig is the standard range for the signal. We have Table 7.1, another reference. Control valves respond relatively quickly with typical time constants ranging from 1 to 4 seconds, time constants referring to tau. The general principle of a control valve are demonstrated in 7.2, and it's the schematic of a control valve. We have the valve plug in the seat, we have the spring, we have the valve stem position, we have the diaphragm, we have the air pressure. And we talked about the diaphragm previously. I had this picture, just wanted to show you. You end up having a pipe, you have an inlet flow rate going through the pipe, you have a pneumatic system, this is like a valve, or just like, a hydraulic up and down press. So you would have this little curved line right here. It separates both sides of this pipe. Pushing down the valve would cause it to cease flow inside the pipe. Opening the valve would make the process continuous. Moving on, this is termed the valve stem. After the final control element has been adjusted, the process responds to changes. The process dynamics vary greatly for a wide range of equipment and process industries, with typical dead times denoted as TD and time constants denoted as tau. These are ranging from a few seconds to hours. When the process is by far the slowest element in the control loop, the dynamics of the other elements are negligible. And this situation is common and it's important, and it's shown in example 7.1. So in example 7.1, we end up remembering the transfer function given in chapter 5. Transfer function is always denoted by the input variable divided by the output variable. More specifically, this is y of s divided by x of s. And then we can put some inputs from the table, from 7.2 table, case A, case B, we have our units and we have our elements. We can input this into the transfer function, finally giving us a value. It's worth noting that in example 7.1, we ended up talking about the 63% time, and this has not been explicitly referenced in CBE 360. It has been referenced in CBE 340 more specifically. Moving on with further analysis of the example 7.1, the two cases have been simulated, and the results are plotted in Figure 7.3. The results of the approximate analysis compare favorably with the simulations, and note that for system A, which involves a fast process, the sensor and the final element contribute significant dynamics, resulting in a substantial difference between the true process temperature and the displayed values of the temperature, and which would be used for feedback control. System B, the process dynamics are much slower, and the dynamic effects of all other elements in the loop are negligible, and this is a direct consequence of the time domain solution to the model of the process for step 1 over s input, which has the form differential y of variable t equals constant 1 plus constant 2 times e to the power of negative t over tau 2 plus c1 times e, and so on. And clearly this is a slow mode due to one especially long time constant will dominate the dynamic response. Example 7.1 really wasn't that informative, just informative in the sense that we are still using transfer functions in this chapter. 7.3, selected, controlled, and manipulated variables. Feedback control provides a connection between the controlled and manipulated variables. Perhaps the most important decision in designing a feedback control system involves the selection of variables for measurements and manipulation. Some initial criteria are introduced in this section and applied to the continuous flow chemical reactor in 7.4. figure 7.4. As more details of feedback control are presented, further criteria will be presented throughout parts 3 for a single loop controller, and I believe we are in part 3 of the book. We begin by considering the controlled variable, which is selected so that the feedback control system can achieve an important control objective. The 7 categories of control objectives were introduced in Chapter 7, and they are repeated below. Notice that we ended up saying some of these categories in the beginning of this video in the introduction for Chapter 7. Just to repeat them, the control objectives: safety, environmental protection, equipment protection, smooth plant operation and production rate, product quality, profit optimization, and monitoring and diagnosis. We also have process variables, and then we also have sensor. Then we have a figure. This is the continuous flow chemical reactor we were referring to previously before we touched on this table, and blah, blah, blah. We can move on to the further text. From none to several controlled variables may be associated with each control objectives. Here we consider the product quality objective and decide that most important processes variables associated with product quality is the concentration of reactant A and the reactant effluent. Effluent. Effluent, it means get out. It means the output. The process variable must be measured in real time to make it available to the computer, and the natural selection for the sensor would be an analyzer to the effluent stream. In practice, an on-stream analyzer might not exist or might be too costly, and for the next few chapters we will assume that a sensor is available to measure the key process variables and defer discussion for using substitution inferential variables, which are more easily measured until later chapters. I'm doing good so far, Rita, so let's keep going. The second key decision is the selection of the manipulated variable. Because we must adjust some process variable to affect the process, first, we identify all input variables that influence the measured variable. Input variables are denoted in Chapter 7 as D. It's the load. It means that D is the variable. It can fluctuate, but we also have another variable that can be manipulated, so it's denoted as M, the manipulated variable. And then we go to the second key decision. I think I just said that. The input variables are summarized below for reactors in figure 7.4. So we have our input variables that affect the measured variable. We have disturbances, which is denoted as D, as I was saying. We have the feed temperature, the solvent flow rate, the feed composition before mix, and then we have the coolant inlet temperature. We have adjustable measured variables, or maybe we just have adjustable input variables. That's the correct terminology I'm trying to get at. We got the flow of pure A, and then we got the flow of the coolant. Okay, I'm getting a little bit slipped up on my words. I just wanted to say something funny like pure A. Sometimes that's like when I'm saying that to ChatGPT, he ends up being like pure A, P-U-R, fancy E. Moving on, that's just a little side note, just moving on. We got 6 important input variables are identified and separated into 2 categories. Those that cannot be adjusted, the disturbances, and those that can be adjusted, the manipulated input variables. In general, the disturbance can be changed in other plant units and in the environment outside of it. What is that even saying? Only adjustable variables can be candidates for selection as a manipulated variable. To be an adjustable flow, a valve must influence the flow. In general, manipulated variables include adjustable motor speeds and heater power, and so forth. Some instances of this have shown up in CBE 320. We had adjustable flow rate. Sometimes we end up using RPM, so revolutions per minute. And then we also have the heater power, that's measured in watts. And that's just called power, the power input to the heat exchanger most likely. Criteria for selecting these variables include 1 through 5, the causal relationship between the valve and the controlled variable, the automated valve to influence the selected flow, the fast speed of response, the ability to compensate for large disturbances, and the ability to adjust the manipulated variable rapidly and with little upset to the remainder of the plant. We had subnotes saying required, desired. Moving on, as a method for ensuring that the manipulated variable has a causal relationship on the controlled variable, the dynamic model between the valve and the controlled variable must have a non-zero value. This is stating that the change in Ca over the change in F times A is equal to the proportional gain, Kp. An important aspect of chemical plant design involves providing streams which accommodate the 5 criteria below. I meant to say above, but I'll just put it below anyway, so these are the 5 criteria that I'm talking about, you feel what I'm saying? And then we got examples of cooling water stream and fuel gas which are disturbed and made available throughout plant. 2 potential adjustable flows exist in this example, and based on the information available, either is acceptable. For the present, we will arbitrarily select the valve for reflecting the flow of pure component A, VA. After we analyze the effects of feedback dynamics more thoroughly, we will reconsider this section in example 13.12. Flow of pure component A denoted as VA is kind of something that's weird. I thought it was denoted as F. In conclusion, the feedback system for product quality control connects to the fluid composition analyzer to the valve in the pure A line. The next selection discusses desirable features of dynamic behavior for a controlled system and how these features can be characterized quantitatively. The calculations performed by the controller to determine the valve opening are presented in the next chapter. Moving on, we're going to section FO, control performance measures for common input changes. We'll end up talking about set point input changes. We'll talk about the offset. Everything is important that I'm talking about. You gotta remember this: offset, set point, integral error measures, rise time, decay ratio, the period of oscillation, the settling time, the manipulated variable, overshoot, and we also talk about disturbance input changes. We talk about a step disturbance. We talk about the maximum deviation, the stochastic inputs. We talk about sign inputs. We have several figures that are showing up just in this section alone. We'll talk about the example 2. This looks like a more impactful, a more comprehensive example as opposed to example 1. We'll talk about example 3. And then we'll move on to 7.5. So maybe I just want to move on to 7.5 because I don't want to scroll up. So I'll just make a note saying 7.4 skipped. Approaches to process control, 7.5. There could be many approaches to the control of industrial processes. In this section, 5 approaches are discussed so that more common procedures are placed in perspective. No control, manual operation. Let's talk about no control. Naturally, the easiest approach is to do nothing other than to hold all input variables close to their design values. As we have seen, disturbances could result in large sustained deviations in important process variables, and this approach could be serious effects on safety. And this approach could have serious effects on safety, product quality, profit. It's not generally acceptable for important variables, this no control. Like, why would you not want to control important variables? Important variables means expensive, expensive, expensive. However, a degree of freedom analysis usually demonstrates that only a limited number of variables can be controlled simultaneously because of the small number of available manipulated variables. Therefore, the engineer must select the most important variables to be controlled. Next, we'll talk about the manual control. I don't really want to talk about that right now. Let's go to the on and off control. The simplest form of automated control involves logic for a control calculations. In this approach, trigger values are established and the control manipulations changes state when the trigger values is reached. Usually the state changes between on and off, but it could be high or low values of the manipulated variable. This approach is demonstrated in equation figure 7.12 and was modeled for common examples of on and off type control and room temperature control, heating in example 3.4. While appealing because of its simplicity, on and off control results in continuous cycling, and performance is generally unacceptable for the strict requirements of many processes. It is used in simple strategies as maintaining the temperature of storage tanks within rather wide limits. Continuous automated control, we'll talk about that after we talk about the manual control. When corrective action is taken periodically by operational personnel, the procedure is termed manual or open loop operation. In manual operation, the measured values of process variables are displayed to the operator, who has the ability to manipulate the final control element valve by making an adjustment in the control room to a signal that is transmitted to a valve, or in a physical small plant by adjusting the valve position by hand. And this approach is not always bad or termed low technology, so we should understand when and why to use manual operation. A typical strategy used for manual operation can be related to the basic principles of statistical process control and can be best described when referenced to the data shown in figure 7.11. Along with the measured process variables, its desired value and the upper and lower activation energy are plotted. A person observes the data and takes action only when needed. Usually the decision on when to take corrective action depends on the deviation from the desired value. If the process variable remains within an acceptable range of values defined by action limit, the person makes no adjustment, and if the process variable exceeds the action limit, the person takes corrective action. It's so simple, why would you even insert that into the book? I'm talking to Mr. Wiley. A slight alteration to this strategy could consider the constitutive time spent above or below the desired value, but within the action limit. If the time continuously above is too long, a small corrective action can be taken to move the process variable near the desired value.